In this video, we will continue our exploration of nuclear magnetic resonance spectroscopy. As a means of review, so far we have determined that the number of signals corresponds to the number of proton environments. This is because each proton environment experiences a different effective magnetic field. We've also seen that the chemical shift tells us something about the nature of the proton environment. In this video, we will explore the fact that the size of the signal, or the integration, tells us about the relative number of protons in that environment. To explore this last concept, let us return to the spectrum of 1-bromo-2,2-dimethylpropane, as shown in teaching model number 5. What's different about the spectrum shown here is that the integration line is included. The integration line essentially measures the area under the peak and reflects the number of protons in that particular environment. In the old days, an NMR spectrum was printed out in the paper form, and researchers had to actually measure the height of the line, which reflected the area under the curve. Nowadays, of course, the computer will print something out. But regardless of what is printed out or shown, it's not actually the number of protons, but the relative number of protons. So this is a good example here, where we have one environment showing a chemical shift of around 1, and it has an integration of 7, where another environment with a chemical shift around 3.3, and that has an integration of 1.6. Of course, we need an integral number of protons. So we need to find the ratio of protons, first of all, in these environments, and then we can find the actual number, or at least speculate what the actual number is. So in terms of the ratio, in this case, of course, we only have two things to compare. We can take that 7 and divide by 1.66, which roughly equals 4.4. And of course, that is close to 4.5. So the idea is this is roughly 4.5 to 1. But again, we need a whole number, or an integer. So this would be 9 equal to 2. Now, of course, we already know what it should be. So for instance, these methyl groups, 3 of them, come together to represent 9 protons. And of course, there's another environment where there are only 2 protons. But perhaps you can see that if you didn't already know what the structure was, this information is very helpful in starting to put together the structure of the organic compound. We know that at 1 part per million, we're likely to have methyl groups, and if it integrates at 9, well, then there's probably 3 methyl groups. And then, of course, we have something at 3.3, and of course, this means that there are 2 protons in that environment, likely a CH2 group, and likely that CH2 group is near an electron withdrawing group. So very helpful in helping us determine something about the structure. As a means of practice, let us look at the next exercise. Here the idea is that we want to first of all identify the equivalent hydrogens and then predict what the integration would be. And we'll make a prediction to the nearest whole number. So that we're on the same page, I'm going to show you here the equivalent hydrogens, and I've labeled them according to A and B. Now I'd like you to predict what the integrations would be. Now perhaps you recognize that the first structure is actually the one that we just looked at, the 1-bromo-2,2-dimethylpropane. So of course we would expect that there'd be 9 protons in environment A and 2 protons in environment B. For the next structure, we would expect the integration to reflect roughly a 3-to-1 ratio. Now notice that if we take this whole number ratio, 3 versus 1, again, that doesn't tell us the actual number of hydrogens that are there. So remember, if you're working in the opposite way and you find the integration is 3-to-1, do not assume that you have only 4 protons. It's helpful to actually also reflect on the molecular formula. If you look at the molecular formula and initially you think you have 4 protons and the molecular formula tells you that you have 8 protons, well then of course we would need to take these numbers and multiply by 2. And for the last structure, the ratio would be 1 to 2. Again, the ratio 1 to 2 does not tell us the actual number of protons, but it tells us the relative number of protons.